There's too many applications in 8.5 for the time that we are given. So we're skipping Kramer's rule and covering the other applications today. Okay. On Friday, we have Ashley bringing napkins, Elaine bringing cups, Jason bringing plates, Naomi bringing spoons, Justin bringing unsweetened tea. At least we have the essentials as far as having things to eat on. But if you guys want to sign up for anything specifically now and see what your class is bringing, I'll start it over with Jacob. But once again, you can have a little bit of freedom as long as you bring circular treats, store-bought, and or commercially prepared, aka from a restaurant or convenience store, etc.
So if we make it,
If you bring an Oreo and say, yay, bonus, I'll say, no thank you.
Like, you have to bring at least 2, right?
see, what if I bring a whole plate of homemade cookies, but then I have to
Then
take
I'll
them
say
back?
thank you, and then just someone else can do that.
Oh, but does that still go
What if
on
I
points?
Well, then maybe I'll have to take them back because I can't share them with the class. You know?
But does that still count as bonus points?
Yeah, yeah.
Oh my.
We'll probably give her like put cyanide in
What
it.
if someone's parent
Huh?
chefs and things got it?
Ooh, got him.
Make sure it looks commercially prepared then. There we go.
So if we make cookies, just put them in a Costco thing?
Oh my goodness. Yes,
Shut up!
let's just be obedient, and then we'll be done. Okay, so that's another good life lesson.
Something said that.
Neil already did.
I'll take credit for whatever they do.
Whatever nature has.
Yeah.
Kiddos, P.S. Tomorrow is our work day reviewing for our test on Wednesday. Yes, we're going to have Pi Day. Yes, my classroom will be open starting at 7. However, you don't want to accidentally get your treats mixed in with period 1's treats because then they'll eat all your stuff before your class starts. But we are going to be doing some math tomorrow and getting ready for our test and working, but we'll just have Pi Day treats to coincide. Sound good? It's better than no review day and just test on Wednesday. Alright, let's go find, you guys should have the title, the area of triangles.
Whoa.
You might not have gotten this written down on Friday, but we did talk about it just a little bit. And I said, any 3 points can make a triangle as long as they are not on the same line. If they're on the same line, that's kind of an awkward triangle. However, as long as 1 point is not on the same line, we can make a triangle. Any 3 points, as long as 1 point is not on the same line as the other 2, we will have triangles. So therefore, you guys get how 3 points makes a triangle as long as they're not on the same line. However, that doesn't mean that if you just have 3 random points and you draw a triangle, it would be super easy to find that area. Because for area, the old-fashioned area, we need either angles and or side lengths to help us out. Preferably a base and a height. So if they just give us points, we don't want to go looking for bases and heights if there's another way. And there is. And that way is called set up a matrix. What do you guys notice about the values that are put into the matrix? Who's that guy? The first point, who's that guy? Second point, who's that guy? Third point, and what did they do to fill in the matrix so that it was possible to find a determinant? Just put in 1s for the third column. So we have the 3 x's and the 3 corresponding y's and then 1s, and all we have to do is multiply that determinant once we find it by 1/2. And the part that gets a little confusing in the formula is the plus minus, but the long story short, just make sure the area is positive. If it's a negative, flip the sign or multiply by a negative. If it's positive, keep it the same. So we could think of absolute value, but if you put absolute value bars outside of the determinant, it looks really awkward and messy, and so we don't do it.
So we just find the determinant after we distribute the 1/2?
You could, although it's probably going to be easier to find the determinant first, then do the 1/2.
Okay.
Because if you put the 1/2 in, then the matrix is going to be ugly with lots of fractions, and that's just messy.
Alright.
Alright. So, how do we use it? Ready, set, and go. You guys can get the example down. As you're getting it down, though, what would have been the old-fashioned old-fashioned way to find this area?
Distance formula and cry.
Distance formula would have gotten you like this one, but base wouldn't have been enough. Could have maybe tried to do some sort of trig to figure out that angle, and maybe we could have gotten to that angle. Oh, you know what we could have done? Distance formula of all three sides. Then we could have figured out some sort of law of sines, law of cosines magic. Probably law of cosines.
Yes.
To get an angle. Then we could have used one of our area equals 1/2 BC sine of theta angles. So, three distance formulas, law of cosines, and the area formula, or, praise the Lord, or none of that and instead do what? Now guys, I'm not even going to put the plus minus. We'll figure it out at the end. Long story short, keep the area positive. Let's just do 1/2 times. You guys already thrown your points in the matrix? 1, 0, 1, 2, 2, 1, 4, 3, 1. Is it okay plugging it in? Take our 3 points. Last column of 1s. Now, if on the test on Wednesday, the calculator portion, and it says use your graphing calculator, are you going to solve any of this by hand?
No.
No. If this is homework and it says use your graphing calculator, are you going to do it by hand? No. That's going to take way too much time. Instead, we can plug and chug and in our calculators. Do you remember where? Wait. What is?
Second terminal.
Yeah, determinant. These little absolute value bars mean determinant, not absolute value in math, right? Or in matrix math.
Yes, let's do it right now.
So I hear a few people plugging in their calculator. Let's have at least 2 or 3 concur. That times 1/2. Just determinant, right?
Yeah.
Okay. Yvette has -3 just as the determinant, so then times 1/2 would be -3 halves. Let's get a few more people to back up. Okay, cool. So area is equal to that whole determinant we can make -3. So area equals -3 halves. Dun 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 dun. No.
What?
Did I say? Make
No negatives.
the area positive. So technically, since we don't do absolute values with matrices, we would assign or we would choose in our formula. For this one, it is plus or minus. Once we get down here, we would say, I see the negative. I would need to choose the negative. Then a negative times a negative would be a positive. That's why there's a plus minus. Because then, if you have a negative, you'd multiply by a negative to get a positive. But do you guys see how we could just make it positive at the end if you need to? You know what I mean? Oh, because area, if we're not in calculus talking about above and below area, like area above the curve and area below the curve, that's a calculus thing. This would be a positive area, this would be a negative area. If we're not talking about applying area is always positive. So when the matrix gives us a negative number, we're like, okay, that's cool and all. It gave us the right value of 3, but the matrix wasn't able to give us the correct sign, so we have to make the last action step of making it. Just think in geometry, whenever you were supposed to find the area of a shape, it should have never been it. Does that make sense? So just make the area positive at the end. And to help you with that, what did we just write in our notes?
Plus or minus.
Make sure the area is positive, and if you get a negative, if this helps, if the determinant of your matrix is negative, make it positive. Is that cool? That's a shortcut to the plus or minus. That's a shortcut to the plus or minus. The plus or minus just means make sure it's positive. If it's not, make it positive. AKA multiply by a negative, but make it positive. Okay. Application number 1, how to find area of a triangle. Application number 2. How can we use what we just did with triangles to figure out whether or not 3 points are collinear. Collinear points. How would you know? Now, some of you are going to be like, count up and over and see if it's the same slope, which is very smart. Let me zoom in on these points. But to prove, which is what I'd be asking for in a test, to prove 3 points are collinear, the only way that we could prove with matrices 3 points are collinear is to say, oh, well, if they're collinear, they won't make a triangle, and the only way it won't make a triangle is if the area is, what do you see down here? If the area is 0. 7, 5. If you guys weren't able to get your points, it's -2, -2, 1, 1, and 7, 5. Now, once again, looking at the picture, could some of you tell me whether or not these are collinear?
They don't look like it.
They don't look collinear. Okay, that's an observation. Anyone else try to do something more proving?
It's not 7, 7 or 5, 5.
Exactly. Do you notice that the x and y's are the same with the slope? You probably imagine you go up and you go over. It should be, or it should have gotten to 7, 7. Since it's not 7, 7. Okay, now that's a very logical, like problem-solving trick sort of way. But what I just said is, how do we prove with matrices, which is the point of this application? How would you prove with matrices? You'd say, okay, I have 3 collinear points. Then, if it helps you guys, just think of it this way. Then the area would equal 0. AKA, it wouldn't be a possible triangle. If the area of a triangle is 0, it's not there, it's not a triangle. Now, technically, if you set the area formula equal to 0, what happens when you multiply the 2 on the other side? 2 times 0 is 0, hence why they don't do the area formula entirely equal to 0. They just say the determinant equals 0, which is a shortcut way of saying it. But if it helps, you could think the area is equal to 0. If it helps, you don't have to memorize something extra. The area of a triangle is a circle? No, the area of a triangle is 0. Bless you, bless you. So, use these 3 points. Let me see if I have a page for it. No. Use these 3 points, and let's use the idea of a matrix to show that it's not collinear, as you guys are supposing, right? If we were to go ahead and plug in -2, -2 with the 1, 1, 1 with the 1, 7, 5 with the 1. The question is, if we were to find or start solving the area formula, would it be a number or would it be 0?
Number. Wait, what was your question?
No, that was my question. I was just looking for the actual number.
Oh, 6.
Oh, the determinant 6?
Yeah.
Cool. If you start solving the area formula, the determinant ends up equaling 6, which is not 0. Thus, the points are not collinear. Because according to that work, according to that work, these 3 points can make a triangle, hence they cannot be on the same line. Now, is it going to be a very big triangle? No. It's not. But there's going to be at least a little area in there. Application number 1, area of triangles given 3 vertices. Application number 2, from the area formula you can know whether or not points are collinear. If there's an area, they're not. If there's not an area, they are. So you guys, let's look at another type of application that's kind of like the ones we just saw. Except it's a little bit harder because how many points did they actually give us?
2.
No.
0, 0.
Now we can't just assume 0, 0 though. That's a struggle. Now some of you are like, haven't we done stuff before, like y2 minus y1 over x2 minus x1, and then plug it into point slope formula? The answer is a resounding yes. But what did they say in solving that you're supposed to be using? Not the beginning of the year stuff. We're supposed to somehow use matrices. And if we don't know a point, what are we going to do? Make a point and say, well, I have to figure out u. When you have unknowns in math, this is not a grit and perseverance question, it's more of a use variables question. And if a line passes through all these points, what's true about these 3 points then? Oh, wrong way. They don't form a triangle because they must be on the same line. Which means I could take my 10, 7 with a 1, and my negative 2, 7 with a 1, and my x, y with a 1, and the determinant, if they're collinear, they're on the same line, will have to equal
0.
0. I don't know. I was trying to say 0 static. Can we plug this in our calculator? We can, it's just not going to tell us anything, right? Struggle. Could this show up on the calculator portion of the test and you still have to do it by hand?
Yes.
Sneaky, sneaky, sneaky. Okay, so how would we solve it? What row or column do you guys want to use? Right? Let's practice determinants. I'm going to go fast. I'm going to give you guys a 30-second head start on your mark, set, go.
I don't remember how to do it.
Find determinants. You try main minus opposite, but it might be easier to use cofactors. Remember, circle one, cross out corresponding row column, take what's left with the determinant. I'm putting my little corresponding signs off to the side. You guys want to check out what should have occurred once you started. I have my cofactors written up. Don't forget the minus in front of the middle one. That's the corresponding sign I would put out in front. Some of you might be stuck, but you don't need to be. Once you get here, what do we do?
Main.
Main minus opposite. Don't forget the minus. Main minus opposite. Careful when you're doing main minus opposite. If you subtract the negative, it should change to be an added. Right? You subtract an opposite. Subtract a negative. You might think it's impossible because there are x's and y's, but if you notice the x terms cancel. That helps things out a little bit. 84 divided by 12?
7.
And there's a negative, nope.
No.
A negative over a negative is a positive.
y back into the
Matrix.
yeah, but like the second step. Like
But the problem is the second step when the x's cancel.
oh.
So how do we find x if we need the point? Any ideas? We have y, we need x, but we can't go plug in y because the x's just cancel out anyway. Not the right answer. He came in and dumped it this morning, so I don't know if he turned it off. I don't know. We could. Then what? What were we supposed to find at the very beginning?
Oh.
The equation of the line passing through the points. The question, did we find the equation of the line?
No.
Are you sure? Y equals 0x plus 7? What's the only line that could go through 2 points with a y value of 7? Oh.
Oh.
So it must be the horizontal line y equals 7.
So-
Otherwise it wouldn't make sense going through 2 points with the same y value.
It can be any point ever. That's stupid.
So it can be all the points. X can be any real number. Kind of think about the 0 equals 0 sort of thing. But we weren't looking for points. We were looking for the equation of the line, and we got it. Y equals 0, x plus 7. I know. Tricky, tricky, tricky. Alright. Last application. Yes. I'm going to go check here. Last application. Cryptography? What?
The screen teaches to make things.
Now, kiddos, I need to show you one thing with the cryptography thingamabob up here at the front. The order is a little awkward, little weird, just because I ended up stealing like 2 different tables that were next to each other, and they didn't fit so good, so I put them underneath. But if you notice, it goes A, B, C,
Oh.
D, E, F, G, H, I, J, K, L, M, N, O, P. There we go. So,
What?
I had to put the 2 tables, they were supposed to be next to each other, and if I were you, I would do A is 1, B is 2, C is 3, D is 4, E is 5. You can fit them on your paper better than I did up here.
Or just corresponding numbers.
You could correspond the numbers, but I'm giving you a quick heads up. For homework, you're going to want this written down in your notes. Now, the Arizona just needs to get 1 degree hotter.
Oh.
Then it'll turn on.
Starting like 2
What?
2 degrees.
Write this down at least once in your notes. The good news is on the test on Wednesday, I'll have it up here on the screen for the calculator portion. Once you guys get there, you're going to start with non-calculator, transfer to calculator. Once the first few people go to the second portion of the test, I'll put this up here. So you're not going to have to write it out on your test or anything silly like that. And you're definitely going to want it written down so you can just use your notes in your homework and not have to keep on looking back in your book. Not have to keep on thinking, okay, so if A is 1, then what is N? 1, 2. No. It's going to take forever. Before we get too much deeper into this, and it's really not a deep topic, it's more just kind of giving you guys a peek at how encoded messages can be made more difficult. How technology these days, coding, ciphering, ciphers have had to get way more complicated for online banking, for passwords, for online shopping. So much is done online these days. Hackers are so advanced in their abilities because the technology has made it advanced. This would not be a great way of encoding your banking information online. However, for where coded messages first began, matrix multiplication is a great way for basic ciphers, not is there a line going to the screen? Huh. I think the projector is like a line that's going down.
Besides the one that's by cryptography?
Yeah.
Oh, that's it.
Hit it then.
Down.
Yeah, it's moving down that horizontal line.
Mhm.
Interesting. Anyway, but in the olden days, think like World War I, World War II, the Enigma code. The imitation game where they were talking about? Yeah. Matrix multiplication would have been a great way of encoding messages, and here's the reason why. If you were just to encode a message, just saying A is 1, B is 2, C is 3, why is that not necessarily a great way of encoding a message?
Because it's really obvious. And
It's really obvious that set A equal to 1, B equal to 2, etc. What if you were to say, oh, I'm going to be sneaky and I'm going to make A equal 5 and B equal 6, or A equal 5 and B equal 7 and C equal 9? Why is it still not good? Those are called shift ciphers, technically. You're just shifting the beginning. But why would it still be easy to crack?
So you have to just play around with it for a little bit.
But how could people play around with that? Like, how could they figure out that you chose 5? Maybe you chose 1,000,005. Maybe you chose 93. How are they going to figure it out?
Is it also be repeated over and over?
What's going to be repeated over and over again?
The value representing it.
Yeah, but how are they going to know if they don't know what the message is? If they're trying to break the message, if they're trying to decode it?
Magic.
Does anybody remember the Enigma code, how that one was broken? But how? Every message started with the same greeting. They finally figured it out. And they were able to, once they knew one little part of the message, expand upon it. Now that was a much more complicated message. They had the machine, and then it was always changing, so it was much more complicated. But I was saying that you did a main shift cipher, where it wasn't always changing all the time. How could someone break your message? Are there any letters that would be commonly repeated in most messages that people would send? Probably not X, Y, but E, maybe S's, maybe other vowels like A, E, I, O. Do you think they could just look for commonly repeated letters and say, hey, I bet that's E? Maybe not. Maybe that's S. Maybe not. Maybe that's A, and they could try the different repeated letters and see which one makes sense.
Then all of a sudden,
Shift ciphers can be broken pretty easily because you can look for repeated numbers that are used a lot and say, hey, I bet it's one of the most commonly repeated letters, and then go off of there. And once you break one letter, or once you think you've broken one, you can try it with others and see if actual words appear. This is what matrix multiplication is better than. It's better than the shift ciphers. So before machines started being used to be, or to encipher messages. Real quick, cryptography. Just the study of encrypting messages. Cryptograms is a way of encoding or decoding a message. Here's the long story short with how matrices are going to help improve encoding messages by hand. So not with computers, not with Enigma machines, etc., etc. How can matrix multiplication improve upon by hand encoding? Here's what we're going to do. We're going to write uncoded. Uncoded means strictly A goes with 1, B goes with 2, etc. Take a message, numerically state it based upon A is 1, B is 2, C is 3, etc. So write an uncoded row matrix of n order. Encode by multiplying by an invertible matrix of n by n order. If it's not invertible, then it's impossible to decipher or decode, which would be super annoying. So encode with an invertible matrix, then you can decode by multiplying by the inverse. Long story short, we're going to multiply by an invertible matrix that's going to mess up all the different numbers. And the only way to undo it is to multiply by an inverse, which will undo all of what multiplying just occurred. Multiplying and adding, I should say. So let's go ahead and go check this out. Oh, hey, that's a much better way of putting it. Sorry. Should have showed you that at the beginning. message that we want to encode. So let's say we have a message, meet me Monday. I have no idea. It's from the book. We're just doing it right now. Don't worry, bonus year test is much more fun. Okay, so
Whoa.
did I just say that?
Hint.
Meet me Monday.
What is that?
Hint, hint, hint.
Meet me Monday. That's the message. First of all, our first step, if we're trying to encode it, to get it coded, is to transfer or to numerically state the message using numbers. Now, kiddos, look at what you wrote up above. Why did Meet Me Monday suddenly become 13, 5, 5, 20, 0, 13, 5, 0, 13, 15, 14, 4, 1, 25, 0?
Because it's how we multiply that.
No multiplication happened. Look at your table. Is N 13? And the answer is yes. Is E 5? Yes. Is E 5? Yes. We can keep on going. What's the 0 for? Mm-hmm. So we just assign each of the letters. And why are we ending with a 0? Because we need to finish the matrix. Now, they told us at the beginning to go ahead and encode it, to write them uncoded in the orders of 1 by 3. So that means that we took our message and we said, okay, we split this up into 3. So 1, 2, 3, count the space. 1, 2, 3, count the space. 1, 2, 3, 1, 2, 3. There was only 2 at the end, which is why we went ahead and included a space so that we had a nice set of 3. The reason why we split them up by 3 is because in this specific one, they decided to encode the message with a 3 by 3. So the way that you encode the message, the matrix that you use determines how you split up the letters. So since we're encoding with a 3 by 3, we split the letters up into groups of 3. Now technically, what they're about to show down below is how to take the uncoded, use the encoder in order to make it coded. Except they made it kind of more confusing. They were saying, hey, let's take each row one at a time and let's encode this one, then let's encode this one, then let's encode this one, and let's encode this one. But that's annoying when our calculator can encode it all at once. So even though the book might show, hey, to encode it one at a time, I would say, no. Just make a big old matrix of, let's see, how many sets of 3 do we have? 1, 2, 3, 4, 5. Let's make a 5 by 3, and let's just put everybody in. Each of the separate groups of 3 have their own row in our 5 by 3 matrix. Just make one grand old matrix. What are we going to do with this 5 by 3? Why do we have them grouped by 3s? What are we multiplying it by? 3 by 3, and we needed it to match. But what we're going to do is throw this matrix A into our calculator. We're going to multiply it by matrix B. We're going to take our uncoded message, separated into groups of 3, made into a big long matrix. We're going to multiply it by the encoder. And just to give you a quick example, even though this final matrix is going to be much bigger because they're going to have 5 different rows. Just look at the first row for a second. What happened to 13, 5, 5 when it got multiplied by -1, -1, 1, sorry, +1, -1, 1, -2, 1, -1, and 2, 3, -4. What happened once the matrix multiplication occurred? 13 randomly stayed the same. 5 became a -26, and 5 became a 21. Wait, what? 13 stayed the same, 5 changed to one thing, and then the other 5 changed to another thing? Why did this code just get way harder to break?
Random.
Yeah, it's random. I mean, it's not because it's based on the matrix multiplication, but it appears random in the sense of, guys, up here the e's were repeated, but can we even tell if we just got this handed to us, can we tell that those are both the same letter? We have no idea. And they're negatives all of a sudden? And the numbers just got bigger than the alphabet? Well, maybe they didn't yet, but they're about to. However, you guys are throwing this in your calculator and multiplying the two. Can anybody finish this matrix for me? Throw in the message, multiply it by the encoder. What do you got, Ricky?
Oh, I have a question.
Go ahead.
Alright, I have two. One, you always multiply by
The message by the encoder.
okay. And oh, and on the test, will it have to be by hand? Or will we
No, it's going to be calculated portion. I'm going to give you a coded message, and I'm going to tell you what was used to encode it, and you're going to have to decode what it says.
Wait.
So I'm going to give you this
so
side,
this- Oh,
and I'm going to
so
tell you this thing, and you're going to have to go backwards. Wait, but how do we decode? But we haven't quite done that yet. Did anybody get the rest of the matrix?
Yeah, 33,
Sorry, go back. 3, 3, what?
33, negative 5, 3, 92. 18. Negative
Okay.
2.
I think I lost whatever you were saying. So let me pause just because we're short on time. You would fill in the rest of that coded matrix. The question is, how do you decode?
We multiply by the inverse matrix.
And I have just used,
The inverse of the encoded matrix.
we did the encoder by the, I'm saying my words weird, hold on. You guys are all packed and I get me all flustered. We have the uncoded, the message, times the encoding matrix. To get the coded matrix, how do we undo? Long story short is we have to undo this matrix multiplication. The only way to undo is to go ahead and multiply by a inverse. Now technically I think on the page before we said this guy was A and this guy was B, right? So let's go ahead and make it proper. We won't say multiply by A inverse, we'll say multiply by B inverse. So Caleb has this matrix on his calculator. How would he be able to go back to the original message? If you multiply the left side by B inverse, those cancel. If you multiply the right side by B inverse, you'll get back to the original. And then how do you take the original numbers, I should say, how do you take the original numbers and get them into the letters? If you have the original numbers, how can you get them to letters? A is 1, B is 2, C is 3, D is 4, etc., 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 etc. Kiddos, good job. Homework. It is listed online, section 8.5. Attempt for tomorrow. I do have, in case you're like, wait, that was way too fast. I do have an example entirely worked out of how to get a message into the uncoded, how to encode it, and then how to decode it. I have the whole shabam in there as an example if you guys need it for homework. Otherwise, now, wow, we're letting go on time. Now you guys can see. Thanks you guys too. Emily, have a great trip, kiddo. See you guys in chapel.
Lauren, what did you say? It's not longer.